So we are talking about this law, zeroth law, and now what is this law? It says that if two bodies are separately in thermal equilibrium, right, with a third body, then they are themselves in equilibrium, thermal equilibrium. Okay. And we already know that what is the thermal equilibrium? That if two bodies have same temperature, then they are in thermal equilibrium. Or if two bodies are in thermal equilibrium, then they will have same temperature. This is the definition of thermal equilibrium. Now what we are saying here is, if TA is equal to TC and TB is equal to TC, then TA is equal to TB. Okay. Now if you go by mathematics, it looks very simple. A is equal to C, B is equal to C, then A is equal to B. Right. But then why is the need of this law? Why do we need this law? तो इसमें जो है सबसे पहले what you have to see is we are talking about thermal equilibrium, not about mathematics. Okay. So we want to put the same thing in the, you can say, physics, in the reality. So if TA is equal to TC and TB is equal to TC, then TA is equal to TB. But what is the need of this? That is important. Now, sometimes I drop it from the class, but let us discuss this time. Now, when do you say that two systems are in thermal equilibrium or they are in equilibrium? Okay. Now, as you know, the whole world is, even if it is in equilibrium, their interaction keeps on going on. This is a very fundamental principle. Even when you think that there is no exchange is taking place, in everything is interacting with everything else. Right? There is always some interaction is there. Now what may happen is, when this interaction take place, there can be microscopic fluctuations. So there are two bodies which are lying isolated from the system, from the surrounding. And let us go by a diagram. So you have a system like this. Okay. And there are two bodies here, one here A and one is B here. Now this whole thing is isolated, which means that there is no effect of the surroundings on this system. Okay. And but these two bodies, even if they are at the same temperature, there may be some flow of energy here and here. And we know because of radiation this happens. One is radiating heat to other, the other is radiating heat to other, even if there is no air. Okay, so these microscopic fluctuations can be there. Now, when do we say that the system is in thermal equilibrium? When these microscopic disturbances do not lead to change of the system properties. अगर ये सिस्टम जो इसी तरीके से बहुत देर तक पड़ा रहे, there is exchange is taking place. Okay, but at the end of it, maybe after 10 minutes, 15 minutes, or whatever the time duration is, the temperature of the two remains same. Then you can say they are in thermal equilibrium, or they are infinitesimally different from each other. But suppose these interactions are taking place in one direction and one body increases the temperature, the second body drops in temperature, then it is not thermal equilibrium. So what you have to see here is that even when there are microscopic disturbances are taking place, the thermal equilibrium is maintained. The bodies are in equilibrium. Now, when you go mathematically, what happens is that suppose there is some energy shifting. Okay. So, okay, what will happen if there are n bodies in the system and delta U sigma, if you take, this is the change in total internal energy of the system. So there are multiple system, n bodies are there. System is only one. There are n bodies within the system which is isolated, and there is some fluctuation. So the internal energy of each one of them will change. That is equal to delta U, and you sum it up. And what will be the change in entropy? For the time being, we have not talked about entropy, but you take it, that is delta U is equal to TdS. Okay. So when some heat is going to one body, and so what will happen? Its entropy will increase, and the body which is losing the heat, its entropy will drop. Now this is what you are summing up. This is the change in heat. So delta U will be equal to Ti delta Si. So whenever there is some heat given to a body, its internal energy will change by delta U, and its entropy will change by Ti. Sorry, entropy will change by Si. Okay, delta Si, and when you multiply it by Ti, it will be equal to del Ui. Okay, so this will be the equation. Now then there is another thing, because the system is in equilibrium, the entropy of the whole system should also remain, change should be zero, because nothing has changed. System is in equilibrium. So the sum of the entropy should be zero. Now, okay. So what you get is, you can write also this, that you multiply this equation by Tj. Okay. So J is one of the i's. So there are n bodies, 1, 2, 3, 4, 5, 6 up to n. J is one of them. Delta Si means entropy change of body I. Okay. Multiplied by Tj. Tj is constant, because that is a one body, particular body. So you sum it up, you will get, you can put this summation of entropy should be zero, and when you multiply it by Tj, even this should be zero, because Tj can go in, because Tj is same for, you are varying I 1, 2, 3, 4, but Tj is constant through all these. Okay, so it is Tj Si. Now what you do, you subtract this equation from this equation. Subtract from this equation. So you are subtracting basically zero. So what you should get, delta U, sigma of del U should be equal to sigma of Ti minus Tj into del Si. Now this Tj is same, it remains fixed during this summation. Ti is the temperature of each bodies. Delta Si is the entropy change of each body, and this delta Ui is the internal energy change of each body. Now, this even change in internal energy should be equal to zero, because no heat is coming from outside, no energy is coming from outside. So what you are getting is, you get finally this equation. So if we write it like this, uh, let me write here. One is sigma del ui, and your sigma over I is equal to 0. This will be 0 because no energy is coming from outside. So if you sum up the internal change in energy of all the bodies, then it will be equal to 0. Similarly, sigma delta Si will be equal to 0, because the system we are assuming in thermal equilibrium, so entropy change will be 0. This will be. Then your delta Ui is equal to Ti del Si. Okay. So you can write that sigma I Ti del Si should be equal to 0. And when you multiply this equation by Tj, you can also write Ti Tj delta Si should be equal to 0, because Tj is here constant. So using this equation, you can multiply by a constant. And sum of all these equations, you can get this equation. Okay. Now, what does this mean, this equation? Now, if this has to be 0, one solution is that delta Si equal to 0. Then this will be 0. But delta Si equal to 0 means you are assuming that there is no entropy fluctuations. But in reality, there will be. When two bodies are there, they are interacting. So you can't impose this condition that delta Si equal to 0. Because there is change in entropy, really. Then how does this become 0? Now what happens that when you solve this matrix, and with the condition that delta Si is not equal to 0, you are assuming that there is some fluctuation, then what you get is that this matrix, then you determinant of this matrix, this is the must vanish for all values of j. So whatever your j is, that means any body you take up which you are pivoting, you take up any body, right? Ti is of all the bodies, Tj is that of one particular body, and you have this matrix, then this matrix, determinant of this matrix must be 0, because your delta Si cannot be 0. Now what happens is, there is a symmetry break is found here. Now if so according to Jacobi theorem, the determinant of this anti-symmetric matrix is always 0 if n is odd, right? So what happens is that if you have odd number of system with odd number of bodies within a isolated system, then this matrix will always be 0, whatever your TIs are. Okay. Now, if n is even, we find that all the entries must vanish. Ti minus, each temperature Ti should be equal to Tj in order to obtain a vanishing determinant. So what is happening is, we are talking about this determinant. If it is an odd set, then whatever the value of Ti's and Tj's are, Tj is only one of them, okay, fixed. but any one of the TIs, then this will always be 0. But if it is even matrix, then all the TIs should be equal to Tj, which is the actual condition for thermal equilibrium. Thermal equilibrium will be there when all the bodies are having the same temperature. Okay. So mathematically what is happening is that if it's only mathematically what is happening is that if your isolated system contains odd number of bodies, then your system is always in thermal equilibrium whatever TIs are. But when it is even, then all the temperature should be same, equal to one value Tj. Only then it will be in thermal equilibrium. So what that this law do is actually it is used zeroth law solve this odd versus even paradox. Okay. And because it can be used to reduce odd number system to an even number system, so what we do by considering 3 of the n system and applying, eliminating 1 by the application of zeroth law. So what do you say? That we take 3 systems, and if they are in equilibrium, if A is in equilibrium to C, B is in equilibrium to C, then A is equal to B, then you can take out the C. Then you can say A and B are equal. Okay. So you can reduce one of them. Then your even odd system becomes even system. Right. And then again the same condition applies that all the temperatures should be same for thermal equilibrium. Okay. So this is what is achieved by this zeroth law. Okay. So zeroth law in short is resolving the, you can say, the symmetric paradox. Odd and even के बीच में जो कॉन्फ्लिक्ट है उसको रिजॉल्व कर रहा है. And why this is necessary? Because you can always carry on with assume that, because when you transfer everything into mathematics, right, and you do not take this over, then what will happen that sometimes those errors may add up. They may actually blow out. तो इसलिए इसकी नेसेसिटी हो जाती है, क्योंकि अगर आप zeroth law नहीं लेते, so what your theory is saying that if there is an odd number of system bodies in a closed system, isolated system, then all of them are in equilibrium even when their temperatures are not same. Mathematically it is like that. And if it even, then all the temperature have to be same mathematically. So what you are getting, this paradox, when you translate into mathematics. So to resolve that, this law is brought up. Okay. So this is the whole significance of this. And not only the zeroth law is not only valid for thermodynamics, there are other things like volume and pressure condition. I don't know about it, not gone into it, but from where I have taken this article, he is saying that it's not that it's only for temperature, because this symmetry break is happening in other cases also. Like he is saying that in case of volume, when you're talking about volume and pressure and fluctuation in mass and chemical potential, there also you have to put up this law. Of course, it will be defined differently for volume and pressure, and similarly mass and the potential, something like that it will be there. So this is the actual necessity of it. So you can say in general, we see that the zeroth law breaks a certain kind of anti-symmetry which persists in thermal equilibrium when first and second law are considered without zeroth law. So if you do not apply the zeroth law and you apply only first and second law, what you are going to get, there is some anti-symmetry in the application. Okay, so ये है, and beyond this, zeroth law is not used. So that is why everybody puts it in the background, although it is very fundamental, because nowhere else you will be using it. It is only to set this anomaly right that zeroth law is used. Otherwise, nowhere you need to apply this. And that is why what happens, people take it just like that, okay, TA is equal to TB, and sorry, TA is equal to TC, TB is equal to TC, so TA is equal to TB, so this is zeroth law and that's all. No, it's not that. Okay, have you got the point? So even when you have not understood it, at least you can understand this much, that there is something more to it.
Delta SI equal to 0, and then at last we told that it can't be equal to 0. So,
No. I said sigma delta SI should be 0. The entropy of the universe should not change. The system is isolated, it is in equilibrium, that system is not interacting with it is in thermal equilibrium. So the sum of the entropies change should not change, should be 0. But individually, because of fluctuation, entropies would change, because all systems are interacting. Natural thing is that all are interacting. It's not that if two bodies have same temperature, they are not interacting. How does two bodies interact? Even when they have the same temperature, they interact. How do they interact? By radiation. And if you have this, if they are in contact, conduction will also take place. If air is there, some fluid to move, even the convection will also take place. If this whole air is at same temperature, does that mean that there is no movement of air? There is no movement of molecules? It happens. Even when the whole air is at same temperature, the molecules are moving very rapidly. And they have different velocities. They go hit each other, exchange the velocity and everything. Even chemical reactions take place. And outside when you look, nothing is changing. Each species concentration is same, the temperature is same, volume is same, density is same. Because you cannot capture the micro changes. Thermodynamics only talks about macro. We cannot measure individual and every atom. That's not possible. So even when we understand the system from the global point of view or macroscopic point of view, we are able to use it. What is happening inside is mind-boggling. You cannot even put it down. You can't even record it. Forget about if I tell you that this is the room, you can tell me its pressure, you can tell me its temperature, you can tell me its density, you can tell me what is the composition of each gas in that, no problem. When I tell you that, tell me the position of each and every molecule. Can you tell me? Can you write it down? You know how many molecules will be there? We can't even think of capturing them. Right? So ये जो एस्पेक्ट है ना कि दे everything is interacting, and this is what the way now come to the spirituality aspect of it. Nature has built in this thing. Man says that there is no heat exchange between two bodies having the same temperature, but nature says no, nothing doing, everything will keep on changing, because nature is engaged in creation. What is nature? Expressing one into multiple. This is what the nature is. That is what the Indian system say, eko aham bahusyam. मैं एक हूं और बहुत हो जाऊं. How will it happen if they do not exchange? So they keep on exchanging. New and new forms keep on coming. Whatever you do, that exchange will always take place. ठीक है. और ये उसी की बात कर रहे हैं कि जब एक्सचेंज होगा, वो एक्सचेंज अगर ऑड बॉडीज हैं that can keep on going in one direction and they can have a different bodies and still your mathematics says that they are in equilibrium. This is the problem. From here onwards, we will move to first law of thermodynamics. Now, you are quite familiar with this law, but as you would have noticed that we have discussed many things which you didn't know, or at least in the way I told you. Similarly, you will find here that this law has some things which have to be noted. Okay. So first thing is, the law says when a closed system moves through a cycle, net amount of the work done and net amount of heat given to the system by the surroundings, they are proportional to each other. Okay. So let us look at these words, closed system. So first thing is that our system is closed. Only then this law applies. Okay. Then you will ask me, when the systems are open, does the first law apply or not? Yes, it applies even then. But then the equations will be different. Okay. That whole statement will be modified. So your system should be closed. And to begin with, we are assuming that it is moving in a cycle or integral number of cycles. What does that mean? The system comes back to its original position. Now, does that mean the law does not apply when a system moves from 1 to state 2? No, it applies. Okay. Even when the system is moving from state 1 to state 2, the first law is applied. But in the statement, in the definition, we begin with a cycle or a number of complete cycles. Then we talk about net amount of work done by the system on the surrounding. So we are talking here the work which the system is doing on the surrounding. And we are talking about net. That means your work can be flow both direction. Okay. If you have a system here, your work can flow like this, you can flow like this. So this is W1 and this is W2. So W net kya hai? Work done by the system on the surrounding. That will be W1 minus W2. Okay. So we are talking about net. Similarly, there is a heat given Q1 and the heat, the surrounding can give heat to the system can give heat to the surrounding. Okay. But we are talking about Q net. Q net is net amount of heat given to the system by the surrounding. It is Q1 minus Q2. Are you getting it? So each and every word has an importance here. Net amount of heat given to the system by the surrounding. And then they say that it is proportional. So what are the conditions? First is that it should be closed. Second is that it should come back to its original state. Then the net amount of heat given is equal to net amount of work done. Now this proportionality can be converted to equality if you have the same units. So heat in calorie will be equal to work in joule proportional, but if they are in joules, then they will be equal. Okay? So you can write this. So this is your statement, and we write in sigma terms that we add up all the work done by the system over the cycle. You see that we have subscript हमने लगा रखा है उसमें cycle का, cyclic. So you are adding all the work in the cycle, you are adding all the heat in the cycle. Heat is given to the system. If it is flowing in the other direction, it should be taken negative. Similarly, work is done by the system. If the surrounding is doing the work on the system, then it will be taken negative. So that you know, and then you can write total net work done is equal to net heat given to the system. Okay. Now you can just write it like this also. Okay. And you can write it like this also. Different ways of writing it. W is equal to Q, Q minus W equal to 0, or the summation of Q is equal to summation of W, or summation of Q minus summation of W equal to 0. One and same thing. Okay, in different. Now, what does it say? So we take, okay, I'll take up this example. What does it mean actually, this law? You take a tank, and this is a closed tank. You put some quantity here, M1, and some quantity from here, M2 comes out. So what will happen? Let us say in this case, now the amount of water added to the tank, M1 is stored in the tank. So when you add water to the tank, what happens? It gets in and it's added to M, whatever mass is already there. Okay. Now when you remove the amount of water from the tank, let us say M2 you remove, it comes out from M. So it is not that M1 is going in and M2 is coming out from M1. No, no. You give M1, this is added up, is collected there as M. And when you take out M2, it is taken out from that reservoir, it comes out. Okay. Now, what does that mean? That M2 can be greater than M1. You can draw more than you input. That is what you do. You think about your overhead tank in your house. You don't put, one day you don't put any water there. Don't pump any water. What will happen? It already has something. At least for a day you can use that water. M2 will be there when M1 is not there. Next day or in the night, your M1 will keep on be there. You will keep on adding the water and there is no outlet. So what is happening? M1 goes and gets added to M and M2 comes from M. Okay. So now if the water tank comes to its original state, suppose whatever the level is there in water, after next day morning again it is full. Okay. Yesterday it was full, the whole day it worked. Then next day again it is full. Then what can you conclude? That M2 is equal to M1. whatever amount of water you have drawn in the whole day is equal to the amount of water you have added. Okay? So this is what happened. In other words, what you are saying, amount of water is always conserved. You cannot draw water if there is nothing inside. Okay, and if you maintain the same level, then whatever you take out has to be refilled. Same thing that happens with energy. In a body, whatever heat you give, you take this, we will not talk about this. Yeah, you take a body. So this is a body, or you can say system, and this is a closed system. Okay. Now, when you are putting in heat or work, they both go in and get added into internal energy. Internal energy works as a reservoir. When you draw out heat or work, it comes out from the internal energy. Now, if what you have added Q1 plus W1 is equal to Q2 plus W2, then the internal energy will remain same. So actually this law is leading to the definition of internal energy. Energy which is stored inside. So just like in a tank mass is stored, okay, similarly the energy is also stored within a body. Okay, you can give some little energy, take out more, then what will happen? The internal level will go down. You can add more, take out less, then the internal level will go up. Or you can put same amount and draw same amount, then the internal level will remain same. That is just like a tank containing water. But in thermodynamics, the systems contain, so mass conservation will also follow. Okay. Similarly, the energy conservation also follows. Okay. ये है इसका हम और एप्लीकेशन देखेंगे, what is it leading to. So I'll stop here.